AWS Database Fundamentals. Relational Databases 101. A relational database is a collection of data items with predefined relationships between them. These items are organized as a set of tables with columns and rows. Tables are used to hold information about the objects to be represented in the database. Each column in a table holds a certain kind of data, and a field stores the actual value of an attribute. The rows in the table represent a collection of related values of one object or entity. Each row in a table could be marked with a unique identifier called a primary key, and rows among multiple tables can be made related using foreign keys. This data can be accessed in many different ways without reorganizing the database tables themselves. This is what you can expect a table to look like. As we discussed previously, it's a series of columns for specific data values that we call attributes, along with a bunch of rows with the records inside them that we call the tuples. The tuples are identified by their primary key, which in this example is the customer ID. The features of relational databases are as follows. SQL. SQL, or Structured Query Language, is the primary interface used to communicate with relational databases. SQL is used to add, update, or delete rows of data, retrieving subsets of data for transaction processing and analytics applications, and to manage all aspects of the database. The second feature is data integrity. Data integrity is the overall completeness, accuracy, and consistency of data. Relational databases use a set of constraints to enforce data integrity in the database. The third one is transactions. A database transaction is one or more SQL statements that are executed as a sequence of operations that form a single logical unit of work. Transactions provide an all or nothing proposition, meaning that the entire transaction must complete as a single unit and be written to the database, or none of the individual components of the transaction should go through. In the relational database terminology, a transaction results in a commit or a rollback. Each transaction is treated in a coherent and reliable way, independent of all other transactions. And the last one is ACID, or ACID compliance. All database transactions must be atomic, consistent, isolated, and durable to ensure data integrity. The shorthand for these properties is called ACID. Atomicity requires that either transaction as a whole be successfully executed, or if a part of the transaction fails, then the entire transaction will be invalidated. Consistency mandates that the data written to the database as part of the transaction must adhere to all defined rules and restrictions, including constraints, cascades, and triggers. Isolation is critical to achieving concurrency control and make sure each transaction is independent unto itself. And lastly, durability requires that all of the changes made to the database be permanent once a transaction is successfully completed. There are two services provided by AWS that allow you to create and manage relational databases: RDS and Aurora. RDS is a relational database service provided by AWS that gives you the ability to provision, create, and scale a relational database. The administrative headaches are lifted off of your shoulders, and it is all managed by AWS. AWS manages the patching of the database, the backing up of the database, and the management of the database engine being used. Now let's take a closer look at database engines. These are the engines that you can use for your databases in AWS. Aurora and MySQL are the options we would consider if we stick to relational databases. For other options, we have other flavors. MySQL is the top choice in open source relational database management systems. MariaDB is a fork of MySQL that is community developed. PostgreSQL is the second favorite choice after MySQL for an open source database. Aurora is AWS's own fork of MySQL, but it provides additional features and benefits. Aurora provides super fast processing and high availability by virtue of having its own cloud-native database engine. Oracle is the corporate choice, and is the most common platform for use in the corporate environments. And lastly, Microsoft SQL Server is the licensable database with a number of licensing options associated with it. In addition to so many different database engines, you also have a wide choice when it comes to selecting which compute instance you'd like to run your database on. The varying database options offer different performance and allow you to architect your environment based on your expected load. When you create your RDS database, you must select an instance to support your database from a processing and memory perspective, as shown here in this screenshot using the MySQL database engine. Currently, these are the different instance types available to you for each of the database engines, which are categorized between general purpose and memory optimized. Non-relational databases. Let's start off by comparing non-relational databases to relational databases. First of all, it is about how data is managed. In relational databases, you can use SQL, that is simple and lightweight language, for writing database scripts. Non-relational databases do not support it, so you might refer to them as NoSQL databases. The second big difference is structure, how data is stored. In relational databases, data is divided into tables that may have relations between them. With the support of primary keys, triggers, and functions, you are capable of creating complex dependencies between tables. This most likely will represent business model and logic inside the database. NoSQL databases are based on the very simple structures like key value storage or a graph that does not support such relations. There's many benefits to using non-relational databases. The first one is the support for multiple data models. Where relational databases require data to be put into tables and columns to be accessed and analyzed, the various data model capabilities of NoSQL databases make them extremely flexible when it comes to handling data. The second major benefit is that it is easily scalable via the peer-to-peer architecture. It's not that relational databases can't scale, it's just that they can't scale easily or in fact cheaply. And that's because they're built with a traditional master-slave architecture, which means scaling up via bigger and bigger hardware servers as opposed to out, or worse, via sharding. Sharding means dividing a database into smaller chunks across multiple hardware servers instead of a single large server, and this leads to operational administration headaches and so on. Instead, look for a NoSQL database with a masterless peer-to-peer architecture with all nodes being the same. Next comes flexibility. Where relational databases require data to be put into tables and columns to be accessed and analyzed, the multi-model capabilities of NoSQL databases make them extremely flexible when it comes to handling data. They can easily process structured, semi-structured, and unstructured data, while relational databases, as stated previously, are designed to handle primarily structured data. Distribution capabilities. Look for a NoSQL database that is designed to distribute data at global scale, meaning it can use multiple locations involving multiple data centers and/or cloud regions for write and read operations. Relational databases, by contrast, use a centralized application that is location dependent, especially for write operations. A key advantage of using a distributed database with a masterless architecture is that you can maintain continuous availability because data is distributed with multiple copies where it needs to be. With NoSQL, there is virtually zero downtime. The final but certainly no less important key feature to seek in a NoSQL database is zero downtime. This is made possible by a masterless architecture, which allows for multiple copies of data to be maintained across different nodes. If a node goes down, that's no problem. Another node has a copy of the data for easy and fast access. When one considers the cost of downtime, this is a big deal. There are 4 main categories of NoSQL databases which are used for different use cases. They are document, key value, columnar, and graph. Data is represented often as an object or JSON-like document. The flexible, semi-structured, and hierarchical nature of document databases allows them to evolve with application requirements. Document databases store and retrieve documents, and the basic atomic stored unit is a document. A document database contains a collection of key value pairs stored in documents that are both natural and flexible for developers to work with. A graph database's purpose is to make it easy to build and run applications that work with highly connected datasets. Typical use cases for a graph database include social networking, recommendation engines, fraud detection, and knowledge graphs. Let's talk about the basic building blocks of a graph data model. A node represents an entity, which could be a place, person, thing, category, or other piece of data. And relationships represent how two nodes are associated. Looking at the example provided of social media, use profile, which is represented as nodes, and relationships are shown as arrows connecting the nodes with each other. Another example would be that of an organization's personnel database, structured as a graph. The entities are employees and departments, and the edges indicate reporting relationships and the departments in which employees work. A key-value database stores data as a collection of key-value pairs, in which a key serves as a unique identifier with its associated value. The value can be any sort of byte array, data structure, or binary large object called a blob, and works well for storing enormous amounts of data. Key-value stores are the simplest NoSQL databases out there. A columnar stored database stores data using column-oriented models rather than by rows, which makes it suitable for analytical query processing. Columnar databases store data efficiently, which is to say that these are row-oriented databases that store each record in one or more contiguous blocks on the disk. Column-oriented databases store each column in one or more contiguous blocks. Columnar storage lets you ignore all the data that doesn't apply to a particular query because you can retrieve the information from just the columns you want. Some of the popular cloud databases which use columnar storage are Amazon Redshift, Google BigQuery, and Snowflake. A columnar database stores its data by columns, with the data for each column stored together. Now let's look at wide column databases. Wide column databases use a concept called a key space. A key space is kind of like a schema in the relational model. The key space contains all the column families, kind of like tables in the relational model, which contains rows which contain columns. Within a given column family, all data is stored in a row-by-row fashion, such that the columns for a given row are stored together, rather than each column being stored separately. Within AWS, these are the services that you will find associated to non-relational databases. OLAP versus OLTP. Online Analytical Processing, or OLAP, is a system for performing multidimensional analysis at high speeds on large volumes of data. Typically, this data is from a data warehouse, data mart, or some other centralized data store. OLAP is ideal for data mining, business intelligence, and complex analytical calculations, as well as business reporting functions like financial analysis, budgeting, and sales forecasting. The core of most OLAP databases is the OLAP cube, which allows you to quickly query, report on, and analyze multidimensional data. What's a data dimension? It's simply one element of a particular data set. For example, sales figures might have several dimensions related to region, time of year, product models, and more. The OLAP cube extends the row-by-column format of a traditional relational database schema and adds layers for other data dimensions. For example, while the top layer of the cube might organize sales by region, data analysts can also drill down into layers for sales by state or province, city, and/or specific stores. This historical aggregated data for OLAP is usually stored in a star schema or Snowflake schema. Online Transactional Processing, or OLTP, enables the real-time execution of large numbers of database transactions by large numbers of people, typically over the internet. OLTP systems are behind many of our everyday transactions, from ATMs to in-store purchases to hotel reservations. OLTP can also drive non-financial transactions, including password changes and text messages. OLTP systems use a relational database that can do the following: process a large number of relatively simple transactions, enable multi-user access to the same data while ensuring data integrity, support very rapid processing with response times measured in milliseconds, provide indexed datasets for rapid searching, retrieval, and querying, and be available 24/7, 365 days a year with constant incremental backups. Many organizations use OLTP systems to provide data for OLAP. In other words, a combination of both OLTP and OLAP are essential in our data-driven world. Let's compare the two systems. The main distinction between the two systems is found in their names: analytical versus transactional. Each system is optimized for that type of processing. OLAP is optimized for conducting complex data analysis for smarter decision making. OLAP systems are designed for use by data scientists, business analysts, and knowledge workers, and they support business intelligence, data mining, and other decision support applications. OLTP, on the other hand, is optimized for processing a massive number of transactions. OLTP systems are designed for use by frontline workers. For example, these could be cashiers, bank tellers, hotel desk clerks, etc. Or for customers for self-service applications. For example, online banking, e-commerce, and travel reservations. Data warehousing. So what is a data warehouse? A data warehouse is a central repository of information that can be analyzed to make more informed decisions. Data flows into a data warehouse from transactional systems. Relational databases and other sources, typically on a regular cadence, business analysts, data engineers, data scientists, and decision makers access the data through business intelligence tools, SQL clients, and other analytics applications. Data and analytics have become indispensable to businesses to stay competitive. Business users rely on reports, dashboards, and analytic tools to extract insights from their data, monitor business performance, and support decision making. Data warehouses power these reports, dashboards, and analytics tools by storing data effectively to minimize the input and output of data and deliver query results quickly to hundreds and thousands of users concurrently. The benefits of data warehousing are as follows. Decision-making becomes a more informed process with all the analytics and data provided by data warehousing. The quality of data is significantly high, in that data integrity is not compromised in the slightest. Data consolidation is a big part of data warehousing. All of your data is found within one warehouse. Separation is also a very big deal. Separation of analytics processing from transactional databases improves performance of both systems. And lastly, historical data analysis, which allows us to look at data ranging all the way back to many years ago. Amazon Redshift is the data warehouse option available within AWS. Amazon Redshift uses SQL to analyze structured and semi-structured data across data warehouses, operational databases, and data lakes, using AWS-designed hardware and machine learning to deliver the best price to performance at any scale.
Hello everyone and welcome to this lab session. In this session, we will look at how you can create your first RDS database in AWS. So for that, we will go to the Search Console and search for RDS. And here you can see we have the Manage Relational Database service. So let's click on this. So this is how your console looks like for Amazon RDS. And over here you can see you have the databases option. So you can create your first database either going to this databases option or create database option from here. So I will go to the databases option and create database. Now in order to create a database you have two options. Either you can go for a standard create. For this standard create option you have to configure each and everything on your own, considering whatever services you want, what are the VPC networks you want for this particular database. But if you want to create your database with the help of the recommended best practices, then it is recommended that you go for easy create option. But I would recommend to always go for the standard create, as in this option you have the flexibility to control each and every settings that you want for your database. So after that we have the option for engine type. So as you can see, these are the 6 database engine types that Amazon RDS supports. So you have Amazon Aurora, MySQL, MariaDB, PostgreSQL, Oracle, and Microsoft SQL Server. So for this tutorial we will be looking at the most common one, which is MySQL. So let's click on this option, and over here then you have the version, like what version you want. So we will go with the default version, MySQL 8.0.27, and then you have templates. So the first template in the list we have is production. So this template is always used when you have your database up and running and ready to be published publicly or in your private network, and where you want that database to be deployed. So this is the production environment where you want it to be used. Then you have the development and test environment template, where you can have your developer developing some sort of algorithms or logics for the database and tester testing them. And then you have a free tier, so we will be going with the free tier option. But I would like to show one thing over here, that for the production and development test you have an option for availability and durability as well. So what does that mean? So basically, for the deployment option, you can actually create multiple backups of your databases. So as you can see, for the first option you have the feasibility to create a primary database cluster and then 2 readable standby DB instances as well. But if you go for multiple AZ DB instances, in that it will create a primary DB instance for you and then a single standby DB instance in different AZ. So AZ is basically regions, by the way. And then you have the single DB instance option. So this is the most basic one. So you do not have any standby DB instances and you only have a single DB instance to work with. So for the free tier, we actually get this single DB instance. So we will use the free tier as of now. And then in the settings, you have the DB instance identifier. So basically, DB instance is an isolated database environment running in the cloud inside the AWS. Basically, it is a building block of Amazon RDS. So you need to give an identifier name over here. So the name I would take is RDS instances, and then you need to give the credentials. So I will go with the admin username. Then you have the option to auto generate a password, or you can create your own password as well. So I will create my own password over here. The next thing is the DB instance class. So basically, the DB instance class determines the computation and memory capacity of an Amazon RDS DB instance. So as of now, you can see over here that we have burstable classes selected, and these two options, the standard classes and the memory optimized classes, are disabled. The reason is that we are not in the development or test environment or either in the production. So if you enable one of them, you will find that that also gets enabled. So for the free tier, you have burstable classes mode only. And over here you can see that we have dbt2 micro, dbt3 micro and dbt4g micro that can be used. So for this tutorial, we will stick with the basic one, and you can see that these are the two basic ones. So you have dbt2 micro, which provides you one virtual CPU with 1 GB of RAM, and it is not EBS optimized, by the way. And then you have dbt3 micro, so it provides you two virtual CPUs with 1 GB of RAM and a network of 2085 Mbps. So I would recommend going with these settings for dbt3 micro, and then just include the previous generation classes as well. So this option is for those users who have been using this RDS service and have not upgraded to an upgraded version of the DB instance. Alright, so then we have the storage option. So for storage, you have general purpose SSD, provisioned IOPS and magnetic. So we will go with the general purpose SSD for now, and the allocated storage is 20 GB. By the way, you also have the option to auto scale the storage. So if you feel a need, like your database is going to take more than 20 GB, so you can actually enable the storage auto scaling as well. But if it's not required, you can simply just disable it for now. So as you can see, the maximum and minimum that you can go is from 21 GB to a maximum of 16384 GB. So let's just keep it enabled for now. And then you have an important setting, that is the connectivity. So basically, whenever you create a database instance, so as of now, like we are creating a MySQL database, so that needs to be assigned to a particular VPC. Now that VPC is a virtual private network where all of your other resources for AWS also exist. So for now, we will go with the default option, or if you want, you can also create a new one. But it is always recommended that even if you want to create a new VPC, you always go to the VPC console in the EC2 instances and create a VPC there, and then move back to this connectivity option and just select the VPC that you want. So for now, we are going with the default VPC, and whatever resources that you want it to connect with this database particular instance, so you need to make sure that this is the VPC that you also assign to those resources as well. And then moving on, we have the subnet group. So we will keep the subnet group default as well. Same instructions for subnet group. If you want another subnet group for this particular database, so go to the subnet group option in the EC2 instances dashboard and just create a new one for yourself. Then you have an interesting option over here that says public access, so it is selected no for now. So if you select no, only those resources that are inside that VPC can only connect. And if you want to give a public access, for example, if you want to connect to this database from a local host or anywhere from the internet, so you need to give it a public access. So for now we will go with the no option, as we will only be accessing it with the EC2 instance that we will create in one of our next session. And then you have the VPC security group. So for the security group, you can see over here that we have choose existing option, or either you can create a new group. So we will go with the choose existing one, and which is the default one. So you can also see that the previous security groups that we created are also available over here, but we will go with the default option for now. And again, the same instructions that the EC2 instance, if you want an EC2 instance to be connected to this database, you need to make sure that the security group is also the same. And then you have the availability zone. So as we are working in North Virginia region, so the availability zone are all of these. So if you want, you can also select the availability zone as well. But as we are not interested in making a backup, so we will go with the no preference option. Then you have some additional configurations. So by default, it is a point to remember that the databases in AWS, the RDS databases in AWS uses 3306 port by default. So we will keep this same for now. And then it asks you like what is the database authentication mode that you want to use. So we have password authentication, but if you want to apply more layers for security for this database, so you can go for password and IAM database authentication or password and KBROS authentication. So for now we will keep it simple and we will go with the password authentication mode. Then we have some additional configurations. So you can give initial database name over here, then the database parameter group, backup. So if you want a backup, you can also enable some automated backups as well. We will keep it nice and simple and won't enable the backups for now. Then you have the encryption. So encryption is enabled for this, and the AWS KMS key will be used for this encryption. So it is the default provided by AWS itself, so we don't need to worry about it. And then if you want some monitoring and log export, so you can also go with that option as well. Moving on, then it shows you the estimated monthly cost. So as of now we are using a free tier, so we don't need to worry about it. But if you are using a development template or a production template, then you do need to worry about it, because Amazon RDS is going to cost you a lot if you do not consider the changes that you are keeping for your database. So keeping all of these things as settings as shown, let's create this database. Alright, so now you can see that the database is being created and it is in the creating mode. It will take a couple of minutes to get it ready so that the database is ready, and then we can use it for our further applications. So with this, I hope you have got an understanding of how you can configure the settings for your Amazon RDS database in AWS.
DynamoDB. Amazon DynamoDB is a fully managed NoSQL database service that provides fast and predictable performance with seamless scalability. DynamoDB lets you offload the administrative burdens of operating and scaling a distributed database so that you don't have to worry about hardware provisioning, setup and configuration, replication, software patching, or cluster scaling. DynamoDB offers encryption at rest, which eliminates the operational burden and complexity involved in protecting sensitive data. DynamoDB has a rich feature set where you have the following features allowed to you. You have scalability en masse, which is to say that you can scale your DynamoDBs almost endlessly. DynamoDB has great support for serverless apps. DynamoDB supports predictable performance, which means you can tell exactly how your DynamoDB is going to perform when it's going to perform. DynamoDB, along with its huge scalability, has a really high availability, which means that you will never ever struggle in getting access to your DynamoDB. It is ideal for read-heavy applications such as Duolingo. And lastly, DynamoDB supports SSD storage, which means that you have lightning-fast access to your resources. These are the use cases that you can associate to DynamoDB. DynamoDB is used in many gaming applications, web applications, mobile applications, as well as IoT applications, or Internet of Things as it's called. This is the data model that you can expect to find in DynamoDB. Each row is an item. Every item has a primary key, which is split up into a partition key and a sort key. Beyond that, each item has its own attributes, and the schema is defined per the item. AWS DynamoDB supports two types of indexes, the global secondary index and the local secondary index. The global secondary index is an index that has a partition key and an optional sort key that are different from the base table's primary key. It is deemed global because queries on the index can access the data across different partitions of the base table. It can be viewed as a different table that contains attributes based on the base table. The local secondary index is an index that must have the same partition key, but a different sort key from the base table. It is considered local because every partition of a local secondary index is bounded by the same partition key value of the base table. It enables data query with different sorting order of the specified sort key attribute. Local secondary index allows query operation to retrieve several items that have the same partition key value but different sort key values, and one item with a specific partition key value and a sort key value. Consider the following example for a DynamoDB item. You can see the partition key and the sort key that serve together as the primary key for this item. These are a few CLI commands that you can use with DynamoDB. Let's go through them one by one. So the first one is create table, which allows you to create a new table. The second one is a put item, that allows you to add new items or replaces old items in the table. Get item, which returns a set of attributes for an item. The update item, which allows you to edit attributes of existing items. Update table, which modifies the entire table, and list tables, which returns a list of the tables in your account. These are some more CLI commands that you can use in DynamoDB. Let's go through these ones also. So the describe table returns information about the table. Scan reads every item in the table and returns all the items and attributes. Query queries the table based on a partition key value that you provide. Delete item deletes an item based on the primary key. Delete table deletes a table, including all of its items. Batch write item puts or deletes multiple items in one or more tables. And batch read item returns the attributes of one or more items from one or more tables. Throughput in DynamoDB is calculated as the total of the write units and read units used up. So say for example you use 21 write units and 35 read units. The way you'd be charged for this usage is the cost of your total storage consumed plus the charge for the write capacity units per hour and then the charge of the read capacity units per hour, which will make your monthly bill. Both read and write capacity units define the access to the data. DynamoDB supports two capacity models, on-demand and provisioned. On-demand is a good option for applications that have unpredictable or sudden spikes, since it automatically provisions read-write capacity. Provision capacity is suitable for applications with predictable usage, and in combination with DynamoDB auto-scaling, the provision capacity variant can dynamically adjust capacity during periods of high usage. Keep in mind that auto-scaling reacts to usage metrics, so there's typically a delay of at least 1 minute before adjustments can be applied to a table, which might not be fast enough to prevent application errors during steep usage spikes. The choice between DynamoDB on-demand versus provision capacity depends on which is the better fit for your applications. On-demand is good for small applications or for large applications with steep and unpredictable spikes that DynamoDB autoscaling cannot react to fast enough. For most other applications, provision capacity is likely a better option when factoring in cost. Amazon DynamoDB Accelerator is a fully managed, highly available in-memory cache for Amazon DynamoDB that delivers up to a 10 times performance improvement from milliseconds to microseconds, even at millions of requests per second. DynamoDB Accelerator does all the heavy lifting required to add in-memory acceleration to your DynamoDB tables, without requiring developers to manage cache invalidation, data population, or cluster management. Amazon DynamoDB is designed for scale and performance. In most cases, the DynamoDB response times can be measured in single-digit milliseconds. However, there are certain use cases that require response times in microseconds. For these use cases, DynamoDB Accelerator delivers fast response times for accessing eventually consistent data. Dax is a DynamoDB-compatible caching service that enables you to benefit from fast in-memory performance for demanding applications. Dax addresses 3 core scenarios. The first one is, as an in-memory cache, Dax reduces the response times of eventually consistent read workloads by an order of magnitude from single-digit milliseconds to microseconds. The second one being that Dax reduces operational and application complexity by providing a managed service that is API compatible with DynamoDB. Therefore, it requires only minimal functional changes to use within an existing application. And lastly, for read-heavy or bursty workloads, Dax provides increased throughput and potential operational cost savings by reducing the need to over-provision read capacity units. This is especially beneficial for applications that require repeated reads for individual keys. DynamoDB Streams captures a time-ordered sequence of item-level modifications in any DynamoDB table and stores this information in a log for up to 24 hours. Applications can access this log and view the data items as they appeared before and after they were modified in near real time. A DynamoDB stream is an ordered flow of information about changes to items in a DynamoDB table. When you enable a stream on a table, DynamoDB captures information about every modification to data items in the table. The diagram shows the relationship between a stream, shards in the stream, and stream records in the shards. To read and process a stream, your application must connect to a DynamoDB Streams endpoint and issue API requests. A stream consists of stream records. Each stream record represents a single data modification in the DynamoDB table, to which the stream belongs. Each stream record is assigned a sequence number reflecting the order in which the record was published to the stream. Stream records are organized into groups, or shards. Each shard acts as a container for multiple stream records and contains information required for accessing and iterating through these records. The stream records within a shard are removed automatically after 24 hours. Shards are ephemeral. They are created and deleted automatically, as needed. Any shard can split into multiple new shards. This also occurs automatically. It's also possible for a parent shard to have just one child shard. A shard might split in response to high levels of write activity on its parent table, so that applications can process records from multiple shards in parallel. If you disable a stream, any shards that are open will be closed. The data in the stream will continue to be readable for 24 hours. Because shards have a lineage, i.e. they have a parent and children, an application must always process a parent shard before it processes a child shard. This helps ensure that the stream records are also processed in the correct order. If you use the DynamoDB Streams Kinesis adapter, this is handled for you. Your application processes the shards and stream records in the correct order. It automatically handles new or expired shards in addition to shards that split while the application is running.